Well, today we're entering into the final stretch of content between now and the final exam. So we're just basically finishing out chapter 16 and that's it. So today we're going to be talking about 16.4 a little bit, Green's theorem, and then next Monday more Green's theorem, just a different version of that. And then so largely this is all like double integral stuff. And then we'll finish up, the last section will be 16.9. So not that much content left, all things considered. For Green's theorem, you need to define orientation, which in 2 dimensions really isn't so bad. And so there's positive orientation, which we define as going around in a counterclockwise direction. And then there's negative orientation, which we define as going around in a clockwise direction. Of course, this only makes sense if your curves are closed. If you just have like a line segment or something like this, it doesn't really make sense to say I'm going to go around the line segment in a clockwise direction or a counterclockwise direction. So you really need a closed curve in order to have these orientations make sense. And then with that, we have this, the statement of Green's theorem. Green's theorem is a way to evaluate out line integrals in the, some special situation. So you do need a positively oriented, piecewise smooth, simple closed curve. Luckily, a fair number of our problems get that. And then if you have a 2-dimensional vector field, F, which has a first component P and a second component Q, then instead of evaluating out the line integral, you can instead evaluate a double integral, which is a bit easier typically. And so then the rest of the video, right, I just spent trying to explain why this is the case and give you an idea of the proof of Green's theorem and kind of breaking down your region into lots of small rectangles and trying to calculate out kind of this, again, circulation, you could call it, going around in maybe some counterclockwise direction. And if you kind of very carefully add up all of these line integrals, and you try to, again, calculate out maybe like circulation at a point sort of deal, you end up with this quantity Q sub x minus P sub y. And so what Green's theorem becomes is, rather than calculating out the circulation across the entire curve, you can instead sum up the circulation at every point inside of the curve. And it turns out that administratively, right, when you actually go to do these things, that evaluating out a double integral is quite often easier than evaluating out a line integral. And so that's the statement of Green's theorem. All right. Any questions about the pre-class video before we jump into the new stuff for today? All right. And so I did want to maybe take just 2 minutes or so and put this in a bit of context before we get into the class notes that I've prepared for you. Because now this is the 3rd iteration of evaluating out line integrals that we've seen in this class, or really line integrals with vector fields. So at the top here, I've put a box, right? Line integrals with vector fields. These first came up in 16.2, which, by the way, in 16.2, there was another line integral that we sometimes evaluated, a line integral with a scalar function. Those haven't really grown in significance as much as these line integrals with vector fields have. But we did, add up the density or something like this of a spring, and we got the total mass, for instance, or we pretend we were a whale swimming around and eating up plankton, right? And so things like this, right? Line integrals with scalar functions. And then after that, we've basically been focusing on these line integrals with vector fields. So in 16.2, we learned how to evaluate these in the quote unquote normal way, right? By parametrizing your curve, by calculating out this R prime, all that sort of stuff, doing a dot product, and we evaluated these things out. Then in 16.3/16.5, we learned a trick, right? That if you have a conservative vector field, then you can evaluate a line integral a little bit faster, perhaps, using the fundamental theorem of line integrals. So that was the whole f of b minus f of a business. But again, this trick doesn't always work. You need to have a conservative vector field in order to make this work. If it doesn't work, well, then you have to go back to kind of the original method. And now we're learning a second trick of how to evaluate line integrals with vector fields. And this one It really only works in 2 dimensions. We will get a 3-dimensional upgrade in 16.8. It's called Stokes' theorem. But Green's theorem only works in 2 dimensions, and you need to have a closed curve. So that's, again, kind of, this trick doesn't always work, but when it does, it is usually faster. And so these are the 3 different ways that we've been evaluating out line integrals with vector fields so far in our course. All right, so with that, I guess I'll pause. Are there any questions about this before we jump into the notes? All right, so let's go ahead. And I would like to verify Green's theorem for this first one. I'm going to evaluate this line integral out using the old 16.2 method. So this is just by evaluating out the line integral, is how it's denoting that. And then we will instead use Green's theorem, this new content, and evaluate out this line integral using a double integral, right? The one in Green's theorem. All right, so if we were doing this in the 16.2 style, right, we need to first maybe parameterize our curve. So thinking about our curve is a unit circle oriented in a counterclockwise direction. So my unit circle is a circle of radius 1 centered at the origin. We know it has the Cartesian equation x squared plus y squared would be equal to 1, again, centered at the origin. Unit circle means that the radius is 1. And we've seen how to parameterize these things, right? How to get an R of t quite a few times now in our class. So we would kind of use from polar, and we would say maybe x is equal to 1 cosine theta, and y would be equal to 1 sine theta. Again, 1 is the radius, so kind of an r cosine theta, r sine theta sort of business. We've seen this hopefully enough times that you know that this is parametrizing in the counterclockwise direction, right? That if you plug in t equals 0, you start here. If you plug in t equals pi over 2, you go in this direction. T equals pi, you continue on this way, right? This is going around our circle in a counterclockwise direction. So we are kind of, we do have this positive orientation that Green's theorem quite often wants. And then if you want to go around the circle once and only once to kind of get all of your points, right, you probably should have your t range between 0 and 2 pi. All right, so I have my parameterization. With this, we can go ahead and start to kind of plug in some stuff into our line integral. For instance, we see that the y coordinate of my parameterization, the y equals, right, is going to be 1 sine t. I'll probably just write sine t. Negative x is going to be negative cosine of t. So again, just plugging in the x coordinate and the y coordinate of my parameterization. And then I need to dot product that with, and remember this dr is really the same thing as r prime of t dt. So that dr is notation, and what it means is r prime of t dt. So, well, we could maybe spend really quick off to the side here, calculating out r prime of t. So the derivative of cosine is going to be negative sine, and the derivative of sine is going to be cosine. So now on my next line here, we can go ahead and elaborate a little bit more. Plugging in our r prime of t. We also see that this is a t integral, so our bounds should be t bounds, right? And this is where we need to use the bounds for t over here from 0 to 2 pi, right? Because we want to go all the way around the circle. So 0 to 2 pi. And now we're getting to the point where it's time to evaluate. So let's do our dot product here. This is going to be negative sine squared minus cosine squared. And for our first problem of the day, this is quite a nice one, right? Because if you factor out that negative, you have sine squared plus cosine squared, and so that's just negative 1, right? So when I integrate negative 1, I'm going to have t evaluated from 0 to 2 pi. Oops, negative t. There we go. And so I'll have negative 2 pi minus 0. Which again, back in 16.2, we talked about the meaning of this as well, right? If you were to draw out this vector field, y comma negative x, and you were to look at maybe points going around our circle here in this counterclockwise direction, this means that the vector field is actually trying to push the points in the other direction, right? That negative answer means that our vector field is actually working against points circulating in this counterclockwise direction. So that's what's going on here if we were to kind of draw a full picture with our vector field and the circle and everything. So I'm not really concerned about a negative, right? Sometimes I'm concerned about getting a negative like for volume or for something like this, but here, right, there's a real legitimate reason to have a negative answer. All right, not too bad. Let's go ahead and evaluate the same integral by using a double integral from Green's theorem. So again, for Green's theorem, it says that if you have a vector field, PQ, and we'll go ahead and set it up kind of similar to what we have here, that this is equal to the double integral of Q sub x minus P sub y dA. And the big thing is that there's kind of, right, when we're doing a line integral, there's some curve that we're integrating across. But when you're doing some double integral, there's a two-dimensional region. And so in my case, right, the line that we're integrating across here is the circle. This would be our C. The two-dimensional region that we get in our double integral is everything that the curve surrounds. So this right here would be this D that I'm doing the double integral over. And that's why you really need a closed curve, because you need to kind of completely surround some region in order for Green's theorem to make sense. So in my case, right, I have a P of y and a Q of negative x. Right, my first component, my second component of my vector field, that's my P and my Q there. And so if I was to take the derivative of Q with respect to x, I would get -1, and I need to subtract away the derivative of P with respect to y, that would be 1. And so now at this point, right, I could actually even factor out this -2. And hopefully you remember, right, the double integral of 1 is a nice geometric thing. Does anyone remember what quantity this is? From like 15.2 or so? Area, yeah, exactly. So this is just area, right? So the triple integral of something of 1, right, is volume. The single integral of 1 ds was arc length. The double integral of 1 dA, right, this is going to be area. And so with this, yeah, you can go ahead, and if I saw this on like a quiz or an exam or something like this, right, I know the area formula for a circle. It's pi r squared, right? And so in my case, I have pi 1 squared is my radius of that circle. And so my answer is going to be -2 pi. Of course, certainly if you wanted to, if you had time and you wanted to be, double check or whatnot, you could go ahead and evaluate out, right, that double integral, in which case you would do it in polar, right, because we're over a circle. So of these two here, I would say maybe the second one's a little bit easier, but not by a ton, right? That they both kind of, we were able to do them in a reasonable time frame. I'd like to now give you an example where Green's theorem does save a significant amount of time. So here's a problem. And notice I've given you the phrasing slightly differently. Instead of it just saying, here's a line integral, evaluate it, right? It instead gives us the physical interpretation, right? It says, find the work done. So find the work done by a vector field. So we need to remember that this is one of the key phrases, right, of doing out a line integral. Here's one of the ways that we can write a line integral. So find the work done by this vector field once counterclockwise around the curve given by the picture. So here's our picture here. And so if I'm going around this thing counterclockwise, I'd be going in this direction. And you can see that, well, it's really quite annoying because there's actually like 4 pieces to my curve, right? There's 2 like half circles, a top circle and a bottom circle, as I've denoted here, bottom circle and top circle. And then there's a left line and a right line. And if I was to evaluate out this using line integrals like we did in part A in our previous problem, right? Each one of these needs to be parametrized. So each one gets its own parameterization. The bottom circle is a circle of radius 1. The top circle is a circle of radius 3. You have to be careful because these are kind of going in opposite directions. One's going clockwise and one going counterclockwise. And then there's 2 line segments. So all of these need their own parameterization, their own ranges for t, their own r primes. And when you go and you evaluate out each one of these 4 pieces, you end up with, well, one of them gives you out negative 2 pi, one of them gives you out 18 pi, one of them gives you negative 16, and one of them gives you positive 16. And then when you add all those 4 pieces together, right, you get 16 pi. If you decided to do this method on a quiz or an exam, that's spending basically all of your time, right? So this is, even though it doesn't say, right, that you can't do it this way. I mean, you certainly can. I just showed you, right, that you can feasibly do it this way. It just takes a really long time. We have to know that Green's theorem is one of the tools that we have now in our toolbox that we can decide to use, even though it doesn't say, right, use Green's theorem. It just says, say, hey, find the work. Now you decide, right? Am I doing a 16.2 method? Could I even do a 16.3 or 16.5 fundamental theorem of line integrals method? I don't know, right? But at very least, I can kind of quickly see that because we have a closed curve and we're going around in this counterclockwise direction, that Green's theorem is at least an option. All right, so if I wanted to find this work done by our vector field here, again, we have our P and our Q. The work, well, I'll go ahead and write. Right, work back in 16.2 is defined as this line integral over a vector field. Remember, we had this was denoted in so many different ways, right? We also denoted this as f dot dr, or the working definition, f dot r prime of t dt. There are also things about how this was, you know, p dx plus q dy, right? There's many different ways that we could write down a line integral over a vector field, all of these meaning the same thing. But now, because we see that it's a nice closed curve and everything, we're going to go ahead and decide to use Green's theorem and calculate out our q sub x, so it's going to be 2, minus our p sub y. So the derivative of p with respect to y is going to be negative 2. And so I'm going to have the double integral of 4. Well, last time I skipped out on the integral. So let's go ahead and maybe just get a little bit of practice and evaluate out this in polar. Of course, you could factor out that 4, right, and consider this as an area, right? And so that's certainly legitimate, and I think that would actually save you a little bit of time here. But if I decided to evaluate this out, right, I would see that, well, my region here, my D, is certainly inside of circles, right? It's kind of portions of circles here. And so I would go ahead and decide to use polar. So my Jacobian, r, dr d theta. My thetas would range from 0 to pi, right? Because I'm only on the top half. If I go beyond pi, right, I no longer have a picture down here. So 0 to pi, just the top half. And then my radius is thinking about how do I enter into and how do I exit my region. It seems like I'm going in through my circle of radius 1, and I'm exiting through my circle of radius 3. By now, I hope that we've done enough of these problems that you're confident in just writing r equals 1 for our lower limit and r equals 3 for our upper limit. Of course, if you wanted to really get into the details, right, this r equals 1 is part of this circle, and you could solve it, putting it in polar and solve it for r. So there was a question in chat. Let me just make sure. Isn't q taken to the partial of y? No, so q is with respect to x according to Green's theorem. So you can go back to our notes here where we have this in a box, right? There it is. So q sub x minus p sub y. Good to verify though. Yep, no problem. Okay, so let's go ahead and finish this one up. I noticed that I do have nice constants for my bounds, so I could go ahead and evaluate out my theta integral separately and my r integral separately if you'd like to. In which case my theta integral is just going to give me pi. And let's see, I'm going to have 2r squared, and I need to evaluate that from 1 to 3. So let's see, that's going to be 9 minus 1, so that's going to be 8. So 2 times 8 will be 16, and of course I've got this pi hanging around. That's the exact same answer as I got on the previous page, but it only took me very few steps, right? Very reasonable to be done now on a quiz or an exam or something like this. So again, a lot of these theorems you have to think about, okay, when can I apply these things? Even though the problem may not say, use Green's theorem. All right, any questions on this one here? Well then, let me give you a little bit of notation here. If you see a line integral with a circle through it, and sometimes this circle may even have a little arrow as well, but not necessarily. So, okay, here's one of the ways that we can write down a line integral. You could also write a line integral, right, with like f dot dr or any of these things as well. So these line integrals here are meant to indicate that the line integral is calculated using a positively oriented closed curve C. So let me include my subscripts as well, at least. So instead of it saying that it's oriented in the counterclockwise direction, or that it's going around in the counterclockwise direction, right, it may include this circle through the integral there. And then also, if you, we have another notation for a positively oriented boundary curve of a region D. So if you have some two-dimensional region D, for instance, you can talk about C being the partial of D there. So that's the partial symbol. And that would mean its boundary curve, and again, oriented in a positive direction. So the counterclockwise direction. All right, so we'll see maybe this come up in the next problem or two. Just an FYI kind of, there is another way that you can expand Green's theorem. And so if you're interested in a fun read, you know, it is in the textbook, the extended versions of Green's theorem. We'll be doing one in Monday's class for normal, kind of a different type of line integrals, bringing up something, the idea of flux. But there are other ways of extending Green's theorem. So here's one that is included in our book, but we're not including in the curriculum here at MSU. All right, well then, let's get back to another problem. Here I have a line integral to evaluate. C is the rectangle with these vertices, but notice nowhere in the problem does it say oriented in the positive direction or negative direction or anything like this, right? It's now using that notation, the line integral with the circle through it, to indicate that we're going around in the counterclockwise direction, that we're positively oriented. So maybe I'll go ahead and start this one by sketching a picture, right? 0, 0, 2, 0, 0, 4, and 2, 4. And I think I've done maybe enough of these, illustrated them here, that maybe I can give you guys 2 minutes to work on this one on your own and see how far you can get. Then we'll talk about the result together. All right, let's go ahead and start talking about this one together. This problem is nice. It does say use Green's theorem to start it. So a little bit nicer if this was still show up on a quiz or an exam or something like this. Tells you what method that you should be using. Of course, right, even if it didn't say use Green's theorem, I would not be very interested in evaluating out this line integral with the 4 different line segments that make up its boundary curve there. And so even if it doesn't say use Green's theorem, I'm hopefully, most folks will lean towards that anyway. So we can set this up, right? We need to calculate out our partial derivatives, q sub x minus p sub y. Then we need to decide on how will we integrate, right? With our double integrals, we really have 3 different methods. We could integrate y first, then x, or x first, then y, or we could switch to polar. I think the only really wrong answer here would be polar, right? So polar would be a bit of a pain, just because this is very much not a circular region. And so you really have to separate out your integral a whole bunch depending on where you're entering and exiting and all that sort of stuff. So either y first then x or x first then y, both are completely fine. You can also factor the sign of negative y out a little bit and kind of split this up like we've done previously. Again, you're not gaining a whole lot of time savings with just a double integral here. And so I decided to go ahead and just set this up. I guess the other thing that I should mention here is that I believe that when you take the derivative of p sub y, right? So q sub x minus p sub y. So there's one negative minus p sub y. There's a second negative when you take the derivative of cosine, right? You get negative sign. And then on the inside, right, when you take the derivative of the inside, thanks to the chain rule, the derivative of negative y is negative 1. So there's 3 negatives. So negative, positive, negative. So I believe that this is correct negative for sine of negative y. But it's easy to miss any one of those. All right, so now let's go ahead and evaluate this out. So if I was to integrate with respect to y here, so the 8x is just along for the ride. The integral of sine would be negative cosine. But then there's that extra negative on the inside. So I believe that this should actually be positive cosine. Double check. If we take the derivative, we should get back to where we started, right? So yes, this should be positive cosine there. All right, negative 4 is along for the ride. And again, we just integrated sine of negative y. We figured out that it was going to be positive cosine of negative y. We need to evaluate that from 0 to 4. Then we have an x integral to do. So let's see, for my 8x stuff, when I plug in 4 in for y, I would get cosine of negative 4. And when I plug in 0 in for y, right, I'm going to get cosine of 0, which is 1. Same sort of deal, cosine of negative 4 minus, when I plug in 0, cosine of 0 is 1. So now I'm going to go ahead and take out this constant, right? Cosine of negative 4 times negative 1. That's a constant in both of these. And when I factor that out, what I'm left with is 8x minus 4. And so if I was to integrate that, the integral of 8x is going to be 4x squared. And the integral of negative 4 is going to be negative 4x. And these we need to evaluate from 0 to 2. So let's see. For my 4x squared, when I plug in 2, I get 4. When I plug in 0, I get 0. For my negative 4x, when I plug in 2, I get 2. When I plug in 0, I get 0. And so this is going to be what, 16 minus 8. So I'm going to have 8 cosine of negative 4 minus 1. Of course, you could distribute that if you want and keep on playing with it, but this is where I would probably punch that into my calculator. Again, make sure your calculator would be in radians. to get a final answer. So the last couple that we've done, right, they have been double integrals of just a constant. So I'm talking about like this one here, where we had the double integral of 4, and the one before that, where it was the double integral of -2, right? And in which case, those ones you can use this area trick on. However, it's not all of them, right? Not all of these Green's theorem ones will be just a double integral of a constant. That's certainly nice when it happens, but you could have to evaluate out a double integral just like you've done through all of chapter 15. It's also kind of nice to think about, this Green's theorem problems. They, when you ask a Green's theorem question on the final exam, well, first of all, you get to maybe test whether the student, actually knows when to apply Green's theorem or not. You get some partial derivatives. That was like from 14.3 sort of deal. So you're testing partial derivatives for free sort of deal. And you're also testing a double integral, which you can kind of make either a polar one or a rectangular one or something like this. So that's going to be from 15.3 or 15.4. So you can see that by asking one Green's theorem question, you are actually getting quite a lot of information in these sorts of problems. All right, any questions on this one here before I move on? Yeah. So when you're applying Green's theorem, this is kind of going back to the notes here, that Green's theorem is when you want to evaluate a line integral, you need to do q sub x minus p sub y, or if you want the partial notation, that's fine as well. I believe this is on our formula sheet, by the way. And so I understand that these subscripts, they can be easy to mix up, and which one you're taking an x derivative of or a y derivative of. But yeah, so it should be q sub x minus p sub y. So a partial derivative of q with respect to x and a partial derivative with respect to y for our p. Good. Any other questions? Oh, sorry. Yes. Oh, yes. So this right here is one of the 5 different ways that we have for line integrals. So this again is a line integral. It's not a double integral. So once we switch over and we decide that we're going to use Green's theorem, so then you need to use a double integral, and the double integral of q sub x minus p sub y. Yeah, so if you're going to evaluate out with a line integral, I mean, you can do it this way, but then again, and this is equivalent, it's just a different notation for this. Remember, for any of them, I said that usually I like to switch over to my working notation, the f dot r prime of t dt. But you could evaluate it like this, but then again, because it's a box, right, you're going to have to parameterize those 4 different line segments: the left side of the box, the right side of the box, the top side of the box, and the bottom side of the box. And so it would take a while if you wanted to use that method, but you could. All right, let's go ahead and maybe tackle this one here together. So I have a picture now of some region. C is the boundary of the region shown to the right. And we have some line integral that we're interested in evaluating. So again, here's our p dx and our q dy. This one's a little bit meaner, right? Because it doesn't say use Green's theorem. Of course, our class is all about Green's theorem today, so we're probably leaning towards that already. But again, if you saw this on a quiz or an exam or whatnot, the main things that you need to look out for is that you have a closed region, right? So we have a C that kind of completely surrounds some region, and it needs to be oriented in a counterclockwise direction. And of those two, actually, oh, sorry, yeah, question. Yeah. It could be. But I mean, it also could be, right, we just got that notation. And before that, right, So here's an example of one where there's no notation whatsoever. It just says, hey, find work, right? And you have to remember what work means, right? And then there was also this starting one here, which says calculate out this line integral. Again, no circle in the middle or anything, but then the region that it goes on to describe, right? A unit circle oriented counterclockwise, you realize, okay, well, that does completely surround a region. The unit circle does completely surround, right, this kind of disk. And it's oriented in a counterclockwise direction. So it's one of the ways that it could be given. It's not necessarily guaranteed to be in that way. Yeah, go ahead. So yeah, the question is if it does have that line integral with a circle through it, then should you basically assume that you're using Green's theorem? And I would say that the probability is like 99%. So yeah, this is meant to be a hint that you do have a closed positively oriented curve. That's exactly what you need for Green's theorem. So you're going to be leaning hard towards Green's theorem at that point. It'd be a jerk move not to have a Green's theorem problem once you have that circle involved. Good questions. All right, so let's go ahead, evaluate this one out. Again, we're going to choose to use Green's theorem, even though no one told us to in this problem. Q sub x is going to be 5 minus P sub y is going to be 2. That's not bad at all. So we're back into the kind of relatively nice stuff. Some of these, by the way, would make fine, multiple choice style questions. When they're this fast, it's probably not worth a full standard response style question, but you could go ahead and make a nice multiple choice style problem like this. So 5 minus 2 is going to be 3. Of course, if you take out that 3, you're doing the double integral of 1, and that's just area. So going over here, if I want to evaluate out the area, because you do have to be a little bit careful, right? This is not a 1-by-1 rectangle or a 1-by-1 square, right? And so you could either use the Pythagorean theorem and get that this is going to be root 2. And so it's actually going to be a root 2 by root 2 square. Or, of course, you can break this up into your 4 triangles as well, right? So if I just found the area of one of these triangles, well, that's going to be 1/2 the base times the height. So that's going to have an area of 1/2. And we have 4 congruent triangles. All of them have the same area. So this is going to be 4 times each one of them has an area of 1/2. So at the end of the day, 3 times 2 equals 6. Or again, if you wanted to do root 2 times root 2, that's another way that you could get 2 for the area. So again, a problem like this, probably not standard response worthy, but a perfectly fine multiple choice style question. Sprinkle in a few other answers. I don't know, 2, 3, 5, 6, 8. There you go. All right, any questions on this one? All right, well, one more to go. Kind of bringing things back to 16.2 a little bit. We have a vector field, x comma y. And I'd first like to only use the picture to hypothesize an answer to this. So remember when we were evaluating out these line integrals before, and kind of what they mean, it's how much is the vector field helping to push, kind of in the same direction that the particles are traveling or against. And so in this case, we are going around in a counterclockwise direction. So we can imagine a particle starting here and kind of going around in this counterclockwise direction. And remember, if the vector field is helping, that means that this result would be positive. If the vector field is hurting, right, it actually would rather them go the opposite direction, then that would be a negative answer. And if it's neither really helping nor hurting, then the answer will be 0. And so if I was to kind of hone in on a few points here and draw out, right, kind of we have maybe some unit tangent vector t, and we have our vector field F. Maybe at this case right here, it does look like that angle is obtuse. It does look like maybe the vector field, although, I mean, more than anything, would rather these particles not be on this curve, I guess. But again, we imagine kind of riding a roller coaster or something. The wind's not strong enough to really knock the roller coaster off the tracks. But maybe it is kind of pushing things back. It is kind of harming a little bit, right? Not by much. It's not quite 90 degrees. But the big thing is, then if we were to compare maybe over here, and again, we have our vector field vector, and we have our unit tangent vector. Now this one, it looks like it maybe is barely helping push in the direction that we're headed, right? It's maybe just a little bit acute. It's a little bit less than 90 degrees. So you can see that there's the symmetry going on. If that one's hurting a little bit, then this one's helping a little bit. And likewise, you can kind of match up any points that you're looking at. If one's helping a little bit, the other one's hurting a little bit. And so I think that all those tiny positives and all those tiny negatives will maybe equal 0 when they're summed up. All right, well, now we would like to confirm our suspicions by evaluating, right? And again, this one does not say use Green's theorem. It does have this little circle, so that's a good indicator. But remember, it's kind of a pain also to parameterize these sorts of ellipses. And so let's go ahead and evaluate this out using Green's theorem. So my P and my Q, let's go ahead and identify those. And we're going to have Q sub X minus P sub Y. So we're going to be doing a double integral of 0 over really any region. No matter what the region is, this one's going to give out 0. So that's how we could prove that, thanks to Green's theorem. All right, well, that's it for today. Next time, we're going to be talking about this alternate version of Green's theorem where we'll bring up flux. So please make sure that you watch the pre-class video before coming on Monday. Otherwise, yeah, enjoy your extra 5 minutes of freedom or whatnot. I'm sure I'll accidentally use that as we progress through this last chapter. So I apologize in advance. All right, have a great weekend, and I'll see you guys on Monday. Thank you, thank you. I did see that there was a question in the chat. Is there a reason to still calculate line integrals by hand if we have Green's theorem? Can we just use that on the final? So you may not have closed curves, in which case, right, you can't use Green's theorem. So we saw plenty of cases in 16.2 where you have, a curve that looks like this that we could parameterize, or maybe a much nicer one, just a line segment. And if they don't surround a region, then you can't use Green's theorem on them. And so, yes, you still need to remember 16.2. Hello.